Hello again, boat builders. This video is part 2 in a series discussing the strength of a hollow mast compared to the solid mast that it would replace. In part 1, we developed a method of assuring that our hollow mast would be equally as strong and stiff. In particular, we showed that the mathematical product E times I is of key importance, where E is the wood's modulus of elasticity and I is the mast's inertia. Stated another way, the hollow mast can have a different value of elasticity and a different value of inertia than the solid mast, but when the product of these values is equal to or greater than the product of the solid version, we can count on the hollow mast being just as strong and stiff. In this video, we will examine several techniques, strategies if you will, allowing one to accomplish this result. In the first example, we keep the elasticity of the hollow mast the same as that of the solid mast, that is, we use the same species of wood, but adjust the inertia by increasing the OD slightly to make up for the loss in inertia resulting from its hollowness. In the second example, we accept the lower inertia of the hollow mast, but instead increase its elasticity by using a stronger species of wood. We can also include the added increase resulting from the laminating process, as discussed in part 1. In part 1, we saw that the strength and stiffness of a mast was greatly influenced by its length. We reasoned that because the hollow mast would normally be built with the same length, we need not consider the consequences of altering the length. There are cases, though, where the length will be changed. In the third example, we examine the effects of adjusting the mast length. And finally, we consider the benefits and dangers of sheathing a mast with fiberglass reinforcement. Of course, these techniques can be combined in different ways depending on the builder's requirements. The initial step for any of the above strategies is to determine the values of E and I for the solid mast specified in the plans, giving us a target baseline. These values would normally not be included in the boat's plans. However, given the species of wood being used, one can look up its elasticity in tables. Here's a table available on the internet that I've used in the past. We see that the elasticity for cypress is 1.44. We used the formula for a circular cross-section to calculate the inertia of the solid mast. The Crosby designed catboat trio specifies a 4 3/4 inch diameter. Using the formula, we calculate the solid mast inertia to be 25. Our first strategy is to adjust the hollow mast OD to make up for the loss of inertia resulting from making it hollow. The amount of loss depends on the ID we choose. For example, if our purpose is to provide an electrical conduit, the ID need only be, say, an inch. With the 1 inch ID for our Crosby mast, we calculate I to be 24.9. We see that compared to the 25 for the solid mast, we can conclude that no OD changes are necessary. However, if the goal is to minimize mast weight, we could increase the ID to give a wall thickness of 20% its outside diameter. 20% being the recommended minimum wall thickness for most wood species in order to avoid thin wall kinking and consequent catastrophic failure. We see that with an ID of 3 3/4 inches giving us the wall thickness of 1 inch, 1 inch making the wall thickness to 20% of the OD, the inertia calculates to be 15.25. So using the strategy of increasing the OD to compensate, we find that by trial and error, we must increase the OD to 5 1/8 inches. That's a 3/8 inch increase. Doing so gives us an inertia of 24.1. That's close enough to the solid mass value of 25. Note, however, that when the OD is increased, the weight of the hollow mast will also necessarily increase, negating some of the desired weight loss resulting from hollowness. Since the weight of a mast is proportional to its diameter, we can use the area formulas to calculate out what that percentage weight loss is. We see that the solid mast calculates out to have an area of 17.75 units, and the hollow mast calculates out to have an area of 9.6 units. That's 8.5 units less than the solid mast. When you work out the percentage, the hollow mast weighs about 54% of the solid mast. And that's about as good as we can hope for. Another strategy would be to accept the lower inertia of the hollow mast and instead increase the mast elasticity. For the catboat trio, we saw the plan specified cypress for the wood with an elasticity of 1.44, and we calculated inertia of 25. This makes the product E times I equal to 36. I will be using Doug fir instead of cypress. Doug fir has an elasticity of 1.83. As explained in part 1, the laminating process increases this value by at least 10%, giving an adjusted value of elasticity equal to 2. Since we want the hollow mass to have the same product E times I as the solid mass in the plans, 36 for trio, we find that the hollow mass inertia can be lowered from 25 down to 18. Using the previous hollow mast with a 1-inch wall, we find that by trial and error calculations, the OD need to be increased by only 1/8 inch, from the plan's 4 3/4 inches to 4 7/8 inches. Compare that to the 3/8 inch increase required if we use just cypress. Note though, although the cross-sectional area is smaller using Douglas fir is more dense than cypress. This results in the weight of both the larger cypress mast and the smaller Douglas fir mast being nearly the same. Another way to make up for length and stiffness losses caused by making the mast hollow is to shorten it slightly. I plan on building a tabernacle mast for my catboat trio. Doing this results in the shortening of the mast's unsupported length. Using my project as an example, let us see how shortening the mast length affects its strength and stiffness and whether any changes to E or I are required. Reviewing, in part 1 we discussed the formulas for Euler strength and the mast stiffness as measured by the deflection formula. Note that the strength changes proportional to the length squared while the deflection changes proportional to the length cubed. Therefore, we will concern ourselves with the mast strength, knowing that the stiffness will always be improved by a relatively larger amount for any decrease in the mast length. As we did before, we first used the formula to find the baseline strength of the unaltered solid mast. We have already calculated E times I for the solid mast to be 36. Inputting 18 feet for the unsupported length, we see that the Euler strength of trio's solid mast is 0.274. We have also calculated that E times I for the hollow mast with the designed 4 3/4 inch diameter, but having only a 1-inch wall thickness, was 25. If we want the hollow mast to have the same strength of 0.274, solving for L, we calculate a hollow mast length shortened by 3 feet to 15 feet. For my catboat trio, this 15-foot mast length puts the tabernacle hinge 3 feet above the deck where I want it to be. I am therefore not forced to increase the mast OD for strength reasons. So we know that our shortened hollow mast will be of equal strength to the solid mast that is 3 foot longer. Just for kicks, let's see how much stiffer this shorter configuration would be compared to the original solid mast. Using the deflection formula, we see that the solid mast with the Euler strength of 2.74 deflects 14.8 units, while the shorter hollow mast deflects only 12.3 units, i.e., it's 17% stiffer. The lesson is that if we choose to shorten a hollow mast in order to make it of equal strength to the solid mast, we benefit with increased stiffness as a freebie. There is one more option that I would like to discuss. Can we reduce the mast weight even more if we sheathe it with fiberglass? My experience makes me answer a qualified yes. Here's the problem. The elasticity of wood and fiberglass are very different. Wood elasticity ranges in the order of 1 to 2, while fiberglass is in the range of 10.5 to 12.5. Because of this large difference, the fiberglass being more stiff than the wood wall it covers will initially take most of the load, and if the thickness of the sheathing is not sufficient, this fiberglass sheathing will fail, resulting in the forces being transferred to the wood. If the mast wall thickness has been decreased expecting the sheathing to take part of the load, it too will subsequently fail. There's a way around this. Make the fiberglass layer sufficiently thick to handle the full load. What we end up with in reality is a fiberglass mast with the wood mold left in place. If we design our fiberglass mast to have the same 4 3/4 inch OD, we find, through trial and error, that our fiberglass sheathing should have an ID of 4 19/32, giving us a wall thickness of 5/32. Note, this strength only applies if we keep the fiberglass annulus from distorting into an oval shape. We must keep the wooden part of our hollow mast thick enough and use well enough position plugs to assure this annular stiffness. In review, what are the takeaways? In part 1, we discussed the advantage of substituting a hollow mast for a solid mast called for in the plans. We determined that if the product of the elasticity times inertia of the substitute hollow mast was equal to or greater than the solid mast being replaced, it would be just as strong and stiff. In part 2, we described 4 ways of altering the inertia, elasticity, and mast length to achieve this equality. Finally, we looked at issues created when making a composite mast. I encourage you to apply the specifications of your project to each of these strategies or in combination, with the goal of achieving the best fit to your goals. In the meantime, I will be working on a hollow tabernacle mast for Catboat Trio. See you soon.